In this lecture, we are going to see about the normal forms of context-free grammar, Unit 4. These are the topics to be discussed: normal forms of grammar, pumping lemma, and closure properties of CFL. So, we all know what is CFG, context-free grammar. If the language is a CFL, then it should have a grammar in some specific form. In order to obtain the form, we have to simplify the context-free grammar. Every language is generated by some grammar in which all the protections are the form of capital A tends to BC and capital A tends to A. Here capital A, capital B, capital C are variables or non-terminals, and small a is a terminal symbol. So we all know the context-free grammar has the main property is the left hand side it should have only one non-terminal, and right hand side it have many terminals and non-terminals. So this is the format of CFG, and if the grammar said to be in the form of Chomsky normal form, that is CNF, if it should satisfy the below two property. The first property is in the right hand side of the production it contains consecutive two non-terminals, that is A tends to BC. This is the first property, and the second property is A tends to small a, that is it have only one terminal symbol. If the production rule of the given grammar satisfy the below two property or condition, then the CFG is called as Chomsky normal form, that is CNF. In order to find the CNF, we need to perform the following operations, that is we have to simplify the context-free grammar by following the below three techniques. The first one is eliminate useless symbols. In this we have to find out the useless symbols. After that we have to remove the useless symbols from the given context-free grammar. So what is the useless symbol in the sense? If the symbols are terminals which don't appear in any derivation of the terminal string. Terminal string is nothing but the given input string that is derived from the start symbol. That symbol is called as useless symbol. That type of useless symbol have to be eliminated from the given grammar. Second technique is eliminate epsilon production. It is very easy to determine, because if the production having the production rule like A tends to epsilon, then it is the epsilon production. Then after that we have to remove that particular epsilon productions from the given grammar. The third technique is eliminate unit productions. So first of all we have to find out what are the unit productions having the given grammar. Then we have to eliminate that particular unit production. Unit productions in the form of A tends to B, capital A tends to capital B. That means the left hand side of the production having only one non-terminal, and right hand side of the production having only one non-terminal. This type of production is known as unit production. So we have to eliminate useless symbol, epsilon production and unit production to simplify the given grammar to obtain the CNF form, that is Chomsky normal form. So see, if the production rule is in the form of CNF, if it should satisfy the below two properties, that is A tends to BC, that means the right hand side of the production should in the form of two consecutive non-terminals, and the second one is right hand side of the production having only one terminal. So is in the form A tends to BC and A tends to A. If the production is in any one of the form, then the grammar is in the form of CNF, that is Chomsky normal form. Before that we have to simplify the given grammar by using three techniques: eliminate useless symbols, eliminate epsilon production, and elimination of unit production. So the grammar is converted into an equivalent CFG which has no useless symbol, epsilon production or unit production. So the safest way to obtain an equivalent CFG is by following the safest order, that is first of all we have to eliminate the epsilon production. After that involved in the process of elimination of unit production, finally we have to eliminate the useless symbols. We will see one by one. The given problem, they are given some grammar. From that grammar we have to eliminate the useless symbol. So first of all we have to find the useless symbol. After that we can easily eliminate the useless symbol from the given production of the grammar. So here there are three productions. The first production is S tends to AB. The second production is S tends to A. Third production is A tends to B. So here consider S tends to A. For the capital A we can substitute small b. So it give the input string is small b. So capital A is the useful symbol. But in case we can consider B, that is S tends to capital B. After that we don't have any input string, that is terminal, for the non-terminal capital B. So here capital B is the useless symbol. So we can eliminate the useless symbol capital B from the grammar. So we can eliminate AB because B is coming along with another variable capital A. So we are in the process of removing AB. So after that we can getting S tends to small a, because we can eliminate AB, which means we have to eliminate the first production, that is AB. So we can get the second production, that is S tends to A. After that the third production is capital A tends to B. Actually we eliminate S tends to A. So there is no need of have to maintain the second production A tends to B. So again we have to remove the third production A tends to B. So for this grammar we are having only one production, that is S tends to small a. So in the last step you can clearly see that the equivalent grammar is given by capital S tends to small a is the only one production we can get after eliminating the useless symbol. So the second concept is elimination of epsilon production. For this we have to find the epsilon production rule in the given grammar, then we can easily eliminate this. We can see the problem. So this is the given grammar. S tends to AB, A tends to small a, capital A, A tends to epsilon, B tends to small b, capital B, and the last production rule is B tends to epsilon. So first of all we have to find out the nullable symbol in the given grammar. Nullable symbol is nothing but in which variable having epsilon production, that symbol is called as nullable symbol. So here capital A tends to epsilon and capital B tends to epsilon. So these two production rules are called as nullable symbols. Those nullable symbols have to be eliminated from the given grammar for the process of elimination of epsilon production. So elimination of epsilon production process is nothing but we can't just eliminate A tends to epsilon. It is not in the correct meaning. We can substitute the value of epsilon for capital A in the given production rule. After that we can write the production rule of the grammar. So the first production is nothing but S tends to capital A, capital B. You can see that in the last line, that is the resultant grammar after eliminating the epsilon production. So first production S tends to capital A, capital B. So the last point, S tends to AB. First of all you have to write the production rule as it is, which was given in the given grammar. So S tends to AB. So in that, for A we can substitute epsilon. So in case for AB we can substitute epsilon for A, we can get capital B alone. So that S tends to capital B. In the same case we can substitute epsilon for capital B in AB, we can get A alone. So that's why in the last step we can write capital S tends to AB, bar A and bar B. Similarly we can do it for the second and third production. So the second production is capital A tends to small a, capital A, capital A. This is the production rule as it is in the given grammar. Then we can substitute epsilon for capital A in the production rule small a, capital A, capital A. In case there are two capital A in the second production, that is A tends to small a, capital A, capital A. So first of all we can substitute epsilon for 1a. After we can substitute epsilon for both a. In case I can substitute epsilon for 1a, I can get small a, capital A. That's why we are writing in the second line capital A tends to small a, capital A, bar small a, capital A. In case we can substitute epsilon for both a, then we can getting only the small a symbol. That's why in the last step of capital A we can writing only one single a. Similarly we can do it for the last step, that is capital B tends to write the production rule as it is in the given grammar, that is small b, capital B, capital B. Again we can substitute epsilon for 1b. in small b, capital B, capital B. So we can get small b, capital B. After that we can substitute epsilon for both capital B. Then we can get only the single small letter b. So this is the resultant grammar after eliminating the epsilon production. So elimination of epsilon production is nothing but we can substitute epsilon value for the particular variable which is having in the given grammar. So we can write after that substitution of epsilon production in the given production rule. Before that we have to write the production rule as it is in the given grammar. Then we can substitute the epsilon for each variable in the right hand side of the given grammar. So this is the process of elimination of epsilon production. The last step in simplification of grammar is elimination of unit production. So we all know what is unit production. In the particular production, the left hand side having only one non-terminal and right hand side of the production having only one non-terminal. That kind of production is known as unit production, which is in the form of capital A tends to capital B. Here A is one variable and B. We will see one problem on elimination of unit production. E tends to T, E tends to E plus T, T tends to F, T tends to T star F and F tends to ID. So in this grammar we can clearly know that the unit productions are capital E tends to capital T and capital T tends to capital F. So we have to eliminate these unit productions from the given grammar. For this, carefully watch. Capital E tends to capital T. So we can go for the capital T production. So capital T produce capital F. So we can go for capital F. So capital F produce ID. So here ID is the terminal symbol. So for capital T we can substitute ID. So the first production, you can see that in the last line the equivalent grammar without unit production is given by E tends to ID. Actually we can substitute ID for capital T for the reason of E tends to capital T, T tends to capital F, F tends to ID. So for capital T we can substitute the value ID. So in the next line T tends to capital F. Similarly do we are going for the production of capital F, F tends to ID. So for capital F we can writing ID. So in the second line T tends to ID, T star F. We can write another productions as it is in the given grammar. The last one is F tends to ID. F tends to ID is not the unit production because ID is the terminal symbol. ID is non-terminal, it is a terminal symbol. So after removing unit production you can see that there is no unit production rule in the given grammar because T is replaced by ID and F is replaced by ID. Now the meaning of this unit production is we can searching for the non-terminal which is having unit production to searching throughout the production rule of the grammar until we can find the terminal symbol. E tends to T, T tends to F. In case F tends to another non-terminal means F tends to capital A means again we can searching for the capital A until we can searching for the terminal symbol. This is the process of unit production. So the next concept is pumping lemma for CFL. Already we are familiar with the concept of pumping lemma. It is mainly used for proving that the given language is not regular. So in this fourth unit they are giving pumping lemma concept for CFL. So let us take capital L be any CFL. CFL is nothing but context free language. So then there exists a constant value n depending only on the language. In that case, if Z is in L, Z is the total input string and the condition is the length of the string greater than or equal to n, then we can split that particular string Z is equal to UV, W, XY, XY, such that the similar third property already we saw in the first unit. In first unit we can split into W is equal to XYZ. We can split the given input string only into 3 parts, but here we can split the given input string into 5 parts, that is U, V, W, X, Y. So the below 3 properties should be satisfied for pumping lemma. Modulus of Vx, modulus meaning here is the length of the particular string. Vx greater than or equal to 1 and modulus Vwx less than or equal to n. And finally for all the values of I greater than or equal to 0, The condition should satisfy u v power I w x power I y, which is also belongs to the language L. So here the concept is the input string Z is splitted up into 5 parts, that is u, v, w, x, y. This is the diagrammatic form of that splitting process. The above they are mentioning S. S is the starting symbol because we can derive the input string from the start symbol of the given grammar to the input string. So S is the start symbol. That S can be splitted up into Z. For that Z we can split into 5 parts, that is u, v, w, x, y. So we can see one problem for pumping lemma. Show that the language is equal to a power n, b power n, c power n. The condition is n is greater than or equal to 1 is not context free language. So to prove context free language we are using the concept of pumping lemma. Always we have to the same problem like we did in first unit. So first of all you have to write the 3 properties 1 2 3 Roman letter 1 2 3 in the first step. After that we can split it up into the given input string into u, v, w, x, y, z, right, and prove that which is not belongs to the given language. So the first step is assume the capital L is context free, because we always proving the concept in contradiction manner. So in the question they are given prove that is not context free, but we are assuming that is context free. In the final step we can prove by in the contradiction manner, reverse manner. So pumping lemma concept, let L be a natural number. So the second step, Z is equal to a power n, b power n, c power n, because the input string is considered as Z. So here the input string is a power n, b power n, c power n, which is equal to Z. So the modulus of S is equal, modulus of Z is equal to, modulus of Z is nothing but the total length of the input string a power n, b power n, c power n. So the power values should be added. So n plus n, the value is 3n. So modulus of Z is equal to 3n, which is always greater than small n. So whenever the input string is greater than the constant small n, we can split the particular input string into u, v, x, y, z. So for that reason we can split a power n, b power n, c power n into u, v, w, x, y. So then Z is equal to u, v, w, x, y, and the 3 properties should be satisfied in the pumping lemma concept. So the third condition is u, v, w, x, y is equal to a power n, b power n, c power n. So here there are 2 conditions, cases. The first case is all the input strings belongs to number of A's, second one is number of B's, and third one is number of C's, because the given language a power n, b power n, c power n. So the second case is we can also write in the combination of a power I, b power I, and b power I, c power j. This combination is also occur. So let us take the first case. So in that first case, number of A's, number of B's, number of C's. So when both v and x are formed by the repetition of single symbol. What is the meaning of this? In the sense, you can clearly see that in the third property, that is u, v power I, w, x power I, y. So except v and x, u, w, y having single terminal at one time, but v power I, x power I having the particular symbol more than one time, repetition of the particular symbol. The same concept given here. V and x are formed by the repetition of the single symbol, that is u is equal to a power I and v is equal to b power I. Then u, v power I, w, x power I, y, which means v power I and x power I having the repetition of any symbol, that is either a or b or c. So assuming I is equal to 0, so z is equal to u, v power 0. This is the condition, third condition, u, v power I, w, x power I, y. So substitute 0 for the I value, u, v power 0, w, x power 0, y. So anything power 0 is equal to 1, so we can got u, w, y. So u, w, y is equal to ai, which is belongs to w, y. So u, w, y contains at most a power I, b, n minus j, c power n, so which is not in the form of the particular language, so which does not belong to the given language. So we proved the given language is not context free for case 1. Similarly we can do for case 2. So here we can take again I is equal to 0, so the same condition will occur, u, w, y. So UWY contains at most a power n minus I, b power n, c power n, which is not the form of u v power I w x power I y, because u v power I w x power I y is belongs to language, but the below result does not belongs to u v power I w x power I y, so which does not belongs to the given language. So the given language is not context free. So to prove the language is context free, we are using the concept of pumping lemma. So the next topic is closure properties of CFL. So there are some properties for each and every language. The first one is substitution. In the word sense, we can substitute one character by another character, or one symbol by another symbol. So let us take an example. S of 0 is equal to 0 power n 1 power n by the condition of n is greater than or equal to 1. So let us take or assume S of 1 is equal to 0011. For the condition if n is equal to 2, in the sense we are getting 0011. So it contains only two strings, that is 00 and 11. But S of 0 contains one or more A's followed by an equal number of B's, that is zeros. A's means one or more zeros followed by an equal number of ones, right? So consider W is equal to 10, not 10, 10. Then S of W is the concatenation of both S of 1 and S of 0, right? Because the first symbol is 1 and the second symbol is 0. So concatenation of S of 1 and S of 0. So S of W is equal to S of 1 and S of 0. So here S of 1 having two values, that is 00 and 11. So first of all, that first string 00 is multiplied with 0 power n 1 power n. So we can get 00 0 power n 1 power n comma. The second input string of S of 1 is 11. So that is multiplied with 0 power n 1 power n. So we can get the second concatenation input is 11 0 power n 1 power n. So this is the concept of substitution. Some of the applications of substitution theorems are there. The first one is union. So let us take L1 and L2 of two CFLs. Then the union of L1 and L2 is nothing but S of L, that is substitution of language, is equal to L1 union L2. This is the concept of the output of the input string is present either in L1 or L2 or both, which are present in both L1 and L2. So the second application of substitution theorem is concatenation. So let us take L1 and L2 or CFLs. Then the concatenation of L1 and L2 is nothing but S of L is equal to L1 concatenation dot operator and L2. Next one is closure, clean closure and positive closure. Clean closure is nothing but S of L is equal to L1 star. Positive closure is nothing but S of L is equal to L1 power plus. And the last application is homomorphism, is nothing but we can substitute one string for another input string. Let us take LBCFL over the alphabet sigma, and H is the homomorphism, that is also over an alphabet sigma. So SB the substitution that replace each symbol A in epsilon by the language consisting of one string H of A. And the next application is intersection. There are two languages L1 and L2 of CFLs. So the intersection of two languages L1 intersection L2, which is also belongs to the particular language, that is S of L of L1 intersection L2. Let us take one example. Here L1 is equal to A power m b power n by giving some condition, and L2 is equal to A power n b power m. We can clearly see that here L1 intersection L2 is not possible, because L1 requires that there be m number of A's and n number of B's, but for L2 requires n number of A's and m number of B's. So L1 is not equal to L1 intersection L2. It's not possible. So the context free grammar is not closed under intersection. Closed means it is not satisfied under the property of intersection. So this is also one theorem. If L is CFL and R is a regular language, then L intersection R is also a context free language, because the language is always CFL and R is the regular language. Both are regular. Then the intersection of the both regular language is always regular. So by using push down automata, we can clearly prove So assume, let us P, capital P for one language, P is push-down automata, and another push-down automata for or regular language. Then we can perform concatenation operator. That is intersection. Intersection is performed by the Cartesian product. So P dash is the new push-down automata by applying the Cartesian product for both push-down automata, capital P and capital A. So the next one is inverse homomorphism. So if H is the homomorphism, then L is the any language. H inverse of L is the set of strings W such that H of W is also in language. And context-free languages are closed under inverse homomorphism. Closed is nothing but context-free language should satisfied or under the property of inverse homomorphism. It can clearly explained by this diagram for inverse homomorphism. Here after getting the input small a, the H of A, H is nothing but homomorphism. The homomorphism of A is placed in buffer. The symbols of H of A are used one at a time from buffer and feed into the PDA which is being simulated, because it is used to check whether the given input string is accepted or rejected by using the stack concept. So while performing the homomorphism, the push-down automata checks whether the buffer is empty or not. If the buffer is empty, then the push-down automata, if the buffer is not empty, the push-down automata cannot read the input symbols and not apply homomorphism. But if the buffer is empty, then the push-down automata read the input symbol from the given grammar and apply the homomorphism and also simulate with the push-down automata by using stack to check whether the input string is accepted or rejected. So the CFLs are closed under inverse homomorphism, and the CFL is not closed under the concept of intersection. So from this, what is mean by normal forms of grammar? We know what is grammar and what is language. When language is said to be CFL, and what is the use of normal form? Because every language is generated by some grammar, so the grammar should have to be simplified by using three techniques. That is the form of normal form. What is a unit production? In the left hand side and right hand side of the production having only one non-terminal. What is pumping lemma, which is used to prove the given language is not regular, and we should satisfy three properties. List out the closure properties, that is substitution. There are some applications in substitutions, that is union, concatenation, closure, positive, clean closure, intersection, homomorphism, inverse homomorphism. And what is inverse homomorphism?